So the next three lessons are completely tied together. The first two are going to be a review of things we've seen before with no calculus whatsoever, and then in the third one we're going to get to some really crazy integrals. The tool that we're learning here is amazing, but it is challenging, so make sure you've got your brains turned on. For the first lesson, I'm going to sort of point out three of the Pythagorean identities. The Pythagorean identities are the things that were connected to the idea that sine squared x plus cosine squared x equals 1. And what I'm doing is I'm just mentioning to you, these are the three that we're really going to be using in the upcoming problems. The idea that 1 minus sine squared x can be changed into cosine squared x, that secant squared x minus 1 is tangent squared, and that 1 plus tangent squared equals secant squared. I know these last two are sort of the same thing, just rearranged. Turns out we're going to be using them in different places. Now, like 58 seconds ago, I said that I wasn't going to put any calculus in this video, and I think I just changed my mind. One little point I want to make here. If you remember what the derivative of arc sine is, arc sine becomes 1 over the square root of 1 minus x squared. Right? Remember that the derivative of arc tangent, x, becomes 1 over 1 plus x squared. And the derivative of arc secant x becomes 1 over the absolute value of x times the square root of x squared minus 1. So the thing I want you to notice, and this is just neat to notice that when it's 1 minus sine squared, it can be changed into cosine squared. That 1 minus sine squared, 1 minus variable squared, is the same structure we see on the bottom of arc sine. Similarly, secant squared minus 1, variable squared minus 1, is the structure that we see, variable squared minus 1, the structure that we see in arc secant. Finally, when you see 1 plus variable squared, 1 plus tangent squared, that's the exact same structure we see on arc tangent. So these identities, it turns out, are going to help us to work through these types of derivatives and integrals. But the rest of this lesson is just about doing transformation, just about simplifying things. So let's get on to some examples of that. So in this first example, I want us to show that the expression 4 minus 9x squared is equivalent to 4 cosine squared u if you use the substitution x equals 2/3 sine u. So I'm just giving you the substitution. I just kind of want you to do some simplifying. So pause the video, try this out, see what happens. So what we should notice is that you're going to get 4 minus 9 times. Now when I do this 2/3 sine u and square it, I'm going to get 4/9 sine squared u. At this point, the 9's are opposite one another. So I have 4 minus 4 sine squared u. If you really want to see the steps, we could factor the 4 out and get this. And then we remember, hey, when it's 1 minus sine squared u, I can change that into cosine squared u. Right? So actually this was a show problem. Like, I mean, if you want to box anything, box everything, because we showed where this thing comes from. So at this point in the video sequence, like, this is the skill that we're working on. This idea of, if you use the right substitution, can you transform one expression into another fairly nice looking expression? So now we're going one step more difficult on that. I'm giving you the substitution in the expression, but I'm not telling you what it is. I'm saying use x equals 5 tangent u to rewrite the expression 25 plus x squared in terms of u, and make it as nice as possible. Right? So pause the video, do that substitution, and see what you end up with. So I'm seeing this being 25 plus 25 tangent squared u. And just like we did last time, we can factor out the 25, be left with 1 plus tangent squared u. And fortunately, that's one of my other substitutions. 1 plus tangent squared u is secant squared u. So this could become 25 secant squared u. So now again, going against what I said earlier, I'll make a quick reference to some calculus here. If we had a problem that was written in this way, if we had some integral that looked like this substitution would let us change it into this. Now that may not be exciting. You may be thinking, well, if I had the integral of this thing, I would just do the integral. True, but it's interesting. If this had been a square root all along, that suddenly is a cyclotic integral, right? Whereas this one at the end, if we had been square rooting all along, we would have gotten 5 secant u, which is interesting. Like that might be easier. We might be able to work with that. So I'm just trying to hint here at the idea that soon, in the third video, we might be doing some strange substitutions and seeing some really neat things happen. So one more for you. Use the substitution x equals 1/2 secant u to rewrite 4x squared minus 1 in terms of u. Once again, pause the video, work through it real quick. So this is going to be 4 times 1/4 secant squared u minus 1. The 4's will eliminate. We've got secant squared u minus 1, and secant squared u minus 1 will give us tangent u. Tangent squared u. So we've seen a few examples here of if we have the right substitution, we can take sort of a binomial expression and turn it into one fairly straightforward trig function. So hang on to that idea. We're going to go through one more review video, and then we'll put the whole thing together in this grand integration technique.